Hi everyone, I'm Arjit from BSMS 2020 batch, and currently I'm doing my summer internship in Leibniz Institute of Astrophysics, Potsdam, Germany, in collaboration with Max Planck Institute. And today I will talk about Fourier transform and FFT, fast Fourier transforms, and different types of algorithm that we generally encounter, and that will be useful in any kind of research. And I will be giving some actual examples like denoising data and how can we calculate derivatives using FFT and all in this particular talk. So I will be stopping in between so that you can ask your questions after each major part I cover. Okay. So yeah, let's begin. So I've made some notes over here. Uh, is it visible? Can anyone just? Okay.
Yes,
Yes.
yes.
Okay. Okay. Cool.
Is it
Yeah.
visible?
So I've given I've already provided you all with my Google Colab notebook. So I'll be covering the same codes. So if you want, you can so like as I'm explaining, you can also try at your end if you are using a laptop or something. And if you want, I can share these notes as well. So this is pretty much what I've written. So I will be explaining with the help of this one. Okay. So yeah. Okay. So first of all, before beginning, to explain what exactly Fourier series or Fourier transform is, we need to understand what exactly is Fourier theorem. So I'm not going to cover any rigorous proofs or anything in this particular talk. It's just to give you a kind of mathematical intuition on this. Okay. So as I've written over here that the Fourier transform simply means that you have a periodic and continuous signal or a function, and you can write it as a summation of sines and cosines. So we know that sines and cosines are orthogonal to each other, right? They form an orthogonal basis, and we are saying that any periodic or continuous signal, you can decompose it in terms of sines and cosines of different frequencies. So that's what the Fourier theorem says. So this is the only thing that we are assuming over here, that we know the Fourier theorem, which says that if we have a periodic and continuous signal, we can decompose it and write it in terms of as a summation of sines and cosines. Okay. So let's begin. So here, this particular, I will be explaining once that all the important parts, and then I will be skimming through the codes. And since you already have the code, you can easily reproduce it. Okay. So this particular cell, as you can see that this is just importing all the important libraries that we are going to use in some of the upcoming codes. Here, this matplotlib, numpy, cborn, and all. So over here, before starting to analyze a particular signal or anything, we are going to make a particular signal, in the sense that we are just generating a signal with the help of Python. So let us consider that we are choosing a signal that has the frequency of 3 beats per second, or you can say that 3 hertz as well. Okay, and ignore this capital F for now. I will come to that later. Now, what is this T? So Fourier transform, it what actually it does is that we have a signal in our time domain. Means at a particular time interval, we get we get some particular signal. So let's say we have timestamps T1, T2, T3 till some Tn, and then with the help of Fourier transform, we want to find out what are the hidden frequencies in that particular data. So I can give a better example that uh, we all listen to music, right? So let's say I think most of us know already that there are different types of signals, like different types of chords and all. So I'm not very much expert in that. So let's say there are things like A sharp, A minor, D and all. So what I know is that A has the frequency of about 440 beats per second, and D has around 220 or something like that. Okay. So let's say if you are listening to just A at once, so it is just a single frequency. It will be very periodic and sinusoidal, as you can see over here. It will be pretty much smooth and nice. Similarly, if you are listening to a particular frequency, then it will be pretty much good. So if I change this F to, let's say, something like 10, then we are increasing the frequency, so wavelength will decrease, so that all of us know. So you can see that wavelength has decreased over here. And if I decrease it, let's say if I'm keeping it as 1, so you can see that wavelength has increased. So higher the frequency, lesser the wavelength. Simple thing. Now if we are listening to the mix of two particular beats, let's say A and D together, we will have a mixture of frequencies, right? So I will show that as well. So let's say I'm taking 3 and 2, like two different frequencies, and I'm running this particular code. So you can see that this is not exactly like the one we are seeing till now. This is something different. Okay. So now, just by seeing, we cannot tell what are the underlying frequencies in this particular sinusoidal graph. Okay. So what can we do? In such cases, we can use Fourier transform or Fourier series, Fourier analysis to find out the hidden frequencies in that. That's what it's all about. Another application of this is that, let's say you are listening to a particular music and there is an annoying high pitch in that. Okay. So that annoying high pitch, you want to remove it. So what you can do, you can just identify what are the hidden frequencies in that particular signal by converting it from time domain to the frequency domain. So when we get the signal, it's in time domain. In the Fourier series, when we use the Fourier series, we go to a frequency domain where we can identify the frequencies. I'll come to that. And then we can, once we are in the frequency domain and we can identify what all signals are there, what all particular frequencies are there, we can just remove the annoying high pitch and then take something called inverse Fourier transform. I'll come to that. And then we will get a nice music instead of that, by removing that annoying high pitch. Okay. So now we have this. I will just use the simpler case first. So yeah, now imagine that this particular signal, this particular thing. Okay, before moving forward, you can see that I haven't, this is going from 0 to 2 and not from -1 to 1. Okay, so just because reason is simple, you can take from -1 to 1 as well. I'm just, this is just an elementary example, so I'm using only the positive values. There is no hidden reason behind it, and these are just plotting and all. Now imagine that this signal is made with the help of some wire with mass m. Now if I am taking this particular wire and started winding it up around a circle. We take a circle and we start winding this particular wire around that circle. Then we will have two different types of frequencies. The first frequency is this frequency, the frequency of this sinusoidal signal. The second will be the winding frequency, means the frequency with which we are plotting, with the frequency with which we are winding that, we are wrapping that particular metal wire with mass m in that particular circle. So here is another code. So what is, you can see over here that, let's imagine that we just take that wire, this whole signal. Okay, we just take this wire of mass m and we just keep it as the diameter of a circle. Okay, so if we are keeping it as the diameter of a circle, obviously there is no winding, so frequency would be 0, of course. So that's what you can see over here, that when sampling frequency is 0, we call it as winding frequency. So this is 0. Now we start to increase the particular frequencies, let's say from 0 to 0.1, then 0.2, 0.3, and so on. You will observe that you will observe that there are many different complicated and nice patterns that you can see over a flower kind of pattern and all. Now there is some red dots in between. So this red dot is basically the center of mass of that particular wire. So obviously when we will wind it up with different frequencies, we will get different kinds of the position of the center of mass will change, right? That's what the red dot is signifying. Now if we start observing closely the x coordinate of that center of mass, the red dot, you can see that here it's exactly at 1. So obviously if we start at 0, if we keep the wire at 0 till, let's say 2, because our maximum amplitude is 2, then what will happen? The center of mass will come in between, which is 1, right? So that's what you can see, that it's coinciding at 1. So we are starting from peak. I will draw and show it to you as well later on. As we are increasing, it's coming down. You can see that it's coming close to 0, 0, 0. Now it will remain closer to 0. This is also very close to 0. Again, it's highly symmetrical. So it's again close to 0, again close to 0. But you will see that our original frequency was 3 beats per second, right? So at 3 beats, as soon as we are reaching closer to 3 beats per second. So I will show here, let's say 2.3. So it's at 0, right? Now see over here, 2.4, again near to 0. After 2.6, you can see that it's slightly moving now. See, it's going far away from 0. This is 0 and it's slightly away from it. See, it's going towards 1. See over here. So as soon as the winding frequency matches the original frequency of our sinusoidal signal or whatever signal we gave, we are getting a peak. Okay. So this is a kind of a machinery that we were looking for, with the help of which we can identify what is that particular signal which is hidden inside of this whole weird kind of pattern in this winding case, right? So I will just draw it and show it to you. Just give me a second. What I mean by that. Okay. So before that, just see, look over here that any of the frequencies that you are seeing after 3, everything is close to 0. So just to make sure that there is nothing, there is no other peak, you can just see. I have plotted till 10. Here also you can see that everything is near 0. Okay. Now, okay, just give me a second. Yeah. So I could have made here. Just a second. Yeah. Where is the line? Journey. And line, yeah. Okay. So I showed you earlier that when the sampling frequency was 0, okay, this is the x coordinate, okay, this is the x coordinate, and this particular thing is the timestamp or whatever. This particular thing is the frequency. Now, I showed you that at 0 frequency, since we kept it when the winding frequency was 0, the center of mass was at 1. So let's say we are starting from 1. Okay, this is 1. Then it decreased, and then it will increase. It will keep moving around 0. But as soon as we reach some frequency, let's say 3 beats per second, 3 beats per second, what will happen? We are getting a peak because now the center of mass has slightly moved to some different value, right? And after that, again, it will remain at 0. See, like this. So that's what I mean. And why this thing is coming, why, what about this peak, you can ask this question. So this simply happened because I took it between from 0 to 2. If I would have taken it from -1 to 1, the graph would have been made between -1 and 1. So in that case, the center of mass would be at 0 because it's from -1 to 1 and not 0 to 2. That's why this peak is coming. So this peak won't be there in the other cases, but this peak would be there when the winding frequency matches the sample frequency. Okay. So just to make sure over here that if I take the other case where I was taking one mixed case, right? Just a second. Yeah. So when I was taking the mixed case, which was this one, yeah. Yeah. So it will take few seconds to run this code. Just bear with me. Take some time to run this code because like there are many figures in this. Yeah. So now you can see that we have two frequencies we have taken. First one is 2 beats per second. Second one is 3 beats per second. So let's move towards 2 beats per second. See, till now it's near 0. Here also it's near 0. Now when we reach 2 beats per second, you can see that it's somewhat greater than 0, right? Then near 3 beats per second as well, it's greater than 0. But then it again started decreasing and it's near to 0. So now this is not exactly what Fourier transform is, but this will give you an idea of what exactly I'm talking about, what exactly I'm going to talk about in detail. So I'll take a pause here, and if you have any questions, you can ask right now. Did everyone get it? Okay, cool. So, okay, now I will move forward. What does CMF graph mathematically signify? Yeah. So see, center of mass graph, as I showed you over here, that okay. So mathematically, it doesn't signify anything. It's just a way. It's not the exact Fourier transform. It's just a way to signify that this is kind of a machinery that we are making just to help you to how to explain. Like it's just a kind of machinery to give you like mathematical intuition behind this. Like in actual, this is not what Fourier transform is. I'm going to cover this. Okay. Yeah. So now, till now, we were taking just a simple signal. So we can have some complex signal as well, right? Complex in the sense with imaginary parts and all. So whenever we talk about such cases, we know one thing, that what does e to the power of ix signify? So it is nothing but cos theta, sorry, not theta, since I'm taking, yeah, it's just cos x plus I sin x, right? So since it's cos x plus I sin x, another thing that we know about this is that e to the power I times 1 means we are moving toward in the anti-clockwise direction 1 unit distance, right? E to the power 2 times I means we are moving 2 unit distance in the anti-clockwise direction. Now, let's say we want our this particular equation in such a way that the sampling rate is 1 cycle per second. So if we want to do that, we can write it as e to the power 2 pi I times t. So e to the power 2 pi, why 2 pi? 2 pi simply means that we are covering the whole circumference. And t means the time that we are taking to cover the whole circumference. So it's just 1 cycle per second, that's it. So 2 pi describes one full circle and t the amount of time that passed. Now, it's not necessary that the signal that we are getting just has the frequency of 1 cycle per second. It can have some different frequency. So in that case, we have to identify another term, which is f. F is our frequency, the sampling frequency. So that's why now instead of taking e to the power of 2 pi I times t, it is e to the power 2 pi I f of t, f times t. So this is just for a different frequency. Now, whenever we talk about Fourier transform, we don't talk about the anti-clockwise direction. We talk about the clockwise direction. So it's very simple that if we want to go to clockwise direction, we just have to put a negative sign. Okay. So now we are very, very close to our notion of Fourier transforms, the mathematical intuition behind it. Now you can see that if we have a particular number of samples, let's say n, and the function behind it is some f of t. Okay. So if we multiply this f of t with our original equation that we just now found, then what does this particular thing signify? It signifies that, see, this f of t, what is it doing? When this function f of t is reaching its maxima, this will also reach the maxima. And when this is reaching 0, this whole term will also become 0, right? So that's what, it simply means that the rotating complex number is getting scaled as per the values of f of t. Okay. Now let's say you have some n number of samples and you want to talk about all the particular frequencies starting from k equal to 1 to k equal to n. Because the Fourier theorem says that the original signal, if it is continuous and periodic, then we can decompose it in terms of sines and cosines, right? So that's why we are summing it over all the possible frequencies. K equal to 1 to n, all the possible frequencies and samples. So instead of just taking t randomly, we are taking t of k. So it's just a notation. And n is the another number of samples. So if we are increasing the number, and what is y 1 by n? So 1 by n is simply the normalization factor, nothing else. Now, if we increase the number of samples to a very large size, if the number of samples n is really, really large, then we need not take this 1 by n. Instead, what we can do is that to normalize it, let's say we started getting the signal at t equal to 0 and we are getting till t equal to 1. It's completely fine if you take t1 to t2, then just the scaling factor will change. So it will become 1 upon t1 minus 0. If you are taking from t1 to t2, it will become 1 upon t2 minus t1. That's it. And this summation is getting converted to 0 to t1 integral, and f of t, everything else is same. See, f of t to the power this thing is exactly same, nothing else. This is our Fourier transform, but not exactly. The only difference between this equation and the Fourier transform is that Fourier transform does not have this particular normalization thinking. Now, how can we compensate for that? Logic is simple. Since we are removing the normalization thing, it simply means that the center of mass thing that we were seeing over there, whenever the sampling frequency is matching the winding frequency, that particular pattern that we were seeing over here, it will just get scaled up by that particular amount. That's it, nothing else. So the peak will be more prominent, nothing else, that's it. So you can take this, but actual Fourier transform conventionally is defined in this way. So I've written that we are ignoring the 1 by t1 term just as a scaling factor, that's it. Okay. So now, if you want some if we want to go to a deeper level, so let's say we have this signal itself, the signal that we were talking about earlier, f of x. Now we are writing like in terms of f of x. So this, for those who don't know, this is how we define our inner product. Okay, inner product. So what is the, why we are taking cos x and sin x? That can be one question. So the simple answer behind that is both cos x and sin x form an orthogonal basis. So what does that mean? See, whenever we have a particular function f of x, we can decompose it in terms of x and y, because we know that x and y are form an orthogonal basis. So we simply write in school level, we used to write like this would be, if this angle is theta, this component, the projection of f on x axis would be f times cos theta, and the projection of f on y axis would be f times sin theta. So it's exactly the same. Instead of taking x and y, we are taking a new set of orthogonal basis, which is some u and v, in this case cos kx and sin kx. That's it. Now see, I told with that we can decompose any signal in terms of cosine and sine. So that's what I'm writing it over here. So it should technically go from 0 to infinity, but if we are putting k equal to 0, we will get a constant term. Now what is that constant term? Cos kx will become cos 0, which is 1, times a0, and here this whole term will become 0 because sine 0 is 0. That's it. So that term we have written it over here. A naught by 2 is just a conventional way to write it. That's it, nothing else. So you can just write a naught as well. Everything will get scaled up by 2. That's it. And we are assuming one more thing, that our signal is periodic in 2 pi. Means it's going from minus pi to pi or 0 to 2 pi, whatever way you want to take. I have taken minus pi to pi. Now, the normalization factor in this case is 1 over pi. And what is this ak and bk? This ak and bk simply means the how much amount of this f of x is in cos kx, and how much amount of this f of x is in sin kx. So here uh, here I have tried explaining it again. So we are taking projection of f of x in cos kx direction and projection of f of x in sin kx direction. Okay, and this is the normalization factor, the mod of the norm of cos kx whole square and norm of sin kx whole square. And this is the inner product. So inner product simply means taking the projection of f of x towards cos kx, and similarly for sin kx. So that's how, if you calculate this, what is this norm of cos kx whole square, you will get 1 over pi, and here from minus pi to pi, since the signal is varying from minus pi to pi, and f of x cos kx dx with the help of this particular definition. Similarly for bk. So that's how you can find out the Fourier coefficients, and we can find out what is the amount of f of x in each of the frequencies, starting from a lower frequency to a higher frequency. When we are going from k equal to 0 or k equal to 1 to infinity, means we are covering all the possible frequencies of cos kx and sin kx. Now the frequencies at which this ak and bk are most prominent, we can say that those will be the frequencies where the peak will be coming, right? That's a simple way. Now you can ask one more question, that why I have taken minus pi to pi. I can take from 0 to L also, right? Okay. So if we are taking from 0 to L, then simple thing, instead of being 2 pi periodic, it is now L periodic. So what do I mean by that? I will show one figure. Yeah. So here you can see that it's going from minus L to L, then again it's repeating on both the sides. That's what I mean. Yeah. So f of x is just a naught by 2, and same thing I've repeated, but something is different. Instead of cos kx, I've written 2 pi kx by L. So see, in that particular formula, it was 2 pi periodic. Now it's L periodic, right? So everywhere in place of so we have to add like 2 pi by L factor everywhere. So that's why cos kx term became cos 2 pi by L times kx. That's it. Okay. Similarly, bk sine 2 pi by L kx. And here a naught by 2 is same. And when you are finding out the Fourier coefficients, ak and bk, these are called Fourier coefficients. When you are trying to find this out, here it was 1 over pi, right? Now I said instead of pi, now 2 pi is going to L. So pi will go to L over 2, right? So simply 1 over pi will become 1 upon L over 2, which is nothing but 2 over L. So that's why this 2 over L term is coming here instead of 1 over pi. And here it became 0 to L. That's it. So it's just scaling. If you are taking from minus L to L, you will have to change it accordingly. That's it. Now, let's say we have two different signals, F and G, I will try to explain it in terms of the vector case. So let's say we are sampling it at a particular interval delta x, and we sampled it from the beginning was A and the ending was B, and we started from like the first point on f was f1, then f2, then f3, and so on till fn, and here from g1, g2, g3 till gn. So we can write each of them in this column vector form, and delta x would simply be b minus a upon n minus 1. A simple maths. So if we want to find out the inner product of f and g, what we will get? So inner product means we will have to take G transpose F. So G transpose simply means that we cannot directly take inner product of both the column vectors, right? So we will have to take G transpose, which will convert it to a row form. So that's what happened over here, right? And then it will just simply become G1 F1 plus G2 F2 plus G3 F3 like that. And that's how it became sigma k equal to 1 to n, because it's varying from 1 till n, or in many cases you will see that it varies from 0 to n minus 1 as well. So it will become G1 to Gn, so an F1 to Fn, so it's sigma k equal to 1 to n f of k and gk. If you have one of the functions, or let's say both of the functions complex valued, then what will happen is that you will have to take conjugate instead of this. Simple, like instead of just taking transpose, you'll have to take conjugate. That's it. Now, we don't want our inner product to scale as we increase the number of points. So what does it mean? It means that here we have n number of samples. So if we increase the number of samples to 2n, the number of terms in our inner product will also increase. It will go to 2n. So we don't want that. So just to concise things up, we will multiply it by delta x on both the sides. Fine. Now, if we move on to the complex case, means if we have the complex functions, let's say we will have e to the power of ikx instead of some f of x and g of x. I'm taking example of e to the power of ikx. You can take something else as well. And we know that it's cos kx plus I times sin kx. And we are writing that, let's say this is something equal to psi of k. So now I will try to prove that if the inner product of this psi j and psi k will be 0 unless and until this j is equal to k. Means if j is not equal to k, this will give you 0, and if j is equal to k, this will give you 2 pi. Now, why am I proving this? I am proving this to show you that both this psi j, psi k, means different frequencies of k and j are also forming an orthogonal basis. Okay, so here this f of x can be written as c of k into e to the power of ikx. Now look closely. Instead of going from 0 to L or minus pi to pi, we are going all the way from minus infinity to plus infinity. Now, this c of k is also a complex number, so it can be written as alpha k plus I times beta k, because we know that any complex number can be written in terms of a plus I times b, right? A plus ib. And similarly, we have expanded e to the power ikx as well. Now, what is this ck? Ck also means that how much of the ck is again the Fourier coefficient. So the same logic as before, that how much of f of x lie in psi of x. That will give us c of k, means the projection of f of x on psi of k, f of x on psi of k. Both are different. We are going from time domain to frequency domain. So we are going from f of x to psi of k. So how much of f of x lie in psi of k? It's like that. And this psi of k is e to the power I kx itself. So we can rewrite it in this form, where 1 over 2 pi is again the normalization factor, and c of k is the Fourier coefficient. So now we want to prove that this psi j and psi k are forming an orthogonal basis. So if we are taking from minus pi to pi, psi j and psi k, from the old definition of inner product that I showed you, it will be e to the power of ijx times conjugate of this, which will become e to the power of minus ikx, because conjugate of e to the power of ikx, complex conjugate, will become e to the power of minus I times dx. And then if we multiply things up by simple surge analysis method, and it will become e to the power of I times j minus k times x. Now, what is this j minus k? This belongs to an integer. This is an integer value, right? So if you perform this integral, we know that what is the integral, integral of e to the power of something, then it will be, what is the integral of e to the power something? It is simply that same value divided by the extra factor. So that's why 1 upon I times j minus k came over here, and everything else is same. Limit is again going from minus pi to pi. You can see that if j is not equal to k, then this will give you 0. You can perform this calculation, and if it is equal, j is equal to k, then what will happen? Then this particular term will become 0. So this whole term will become 1. And again, this will go to 0. So you will have to use your L hospital rule and everything, L'Hopital rule. And you can find out that this 2 pi is coming over here. And this is the reason why we are getting this 1 over 2 pi normalization factor over here. Yeah. So before moving on, uh, I'll show you some examples with the help of Python. So just a second. Yeah. So you can see over here that I'm just importing the libraries in the beginning in these particular lines. And after that, these two lines are just to set up the figure size and font size and everything. Not of that much importance. Then what is this dx? This dx is the delta x that we were talking about. Okay. So what was the delta x? That was b minus a upon n minus 1. The small difference between x1 and x2, then x2 and x3 and so on. Now we are defining our function in between minus pi to pi. So that's what I've defined. Minus 1 plus dx to 1 plus dx times L, and L is basically pi. Now what is n quad? So I have taken an example of this kind of function, which is known as a hat function, or you can say a triangular wave. There, to define it properly, I'm dividing it into 4 different quarters. So first will be just 0. Second will be the increasing part. Third will be the decreasing part, and fourth will again be 0. So I'm defining it in such a way that I'm dividing the whole array into 4 different quarters. So that's what this particular thing is doing, which is known as np.floor. Python has a very nice way to do it. N is basically length of the original array that we have defined, which is going from minus pi to pi at an interval of x, at an interval of dx, 0.001. And then we are dividing the whole array into 4 different quarters. And then we already know that the first and the fourth array will just be 0. So the frequencies in that case would be f equal to np.zeros like. So what this zeros like does, this zeros like simply will create an array which has only the 0 value, means 0, 0, 0, 0, 0. Now what will be the length of that array? It will be same as length of x. That's what we are putting inside. You can also use np.ones like, not in this case, in some other case. So np.ones like, what it does, it simply makes an array of the 1, 1, 1, 1, 1 of length x. Now in Python, countings doesn't start from 1, 2, 3 and so on. It starts from 0 unless and until you specify. So here also same thing happens. So first, instead of saying the first quarter, it will be the 0th quarter, then the first quarter, then second, and then the third one. So this increasing part comes between first and second quarter, and the decreasing part comes in the second and third quarter, right? Now see over here, that's what it is doing. So n quarter to 2 times n quarter. So means from the beginning part is 0, then the increasing part, then the decreasing part in the below from 2 times n quarter to 3 times n quarter, and then the 0 part. So that's how we are defining our hat function manually in this case. Then we are plotting that hat function. Okay, this is the first part. Now I will try to decompose that hat function in terms of sines and cosines of different frequencies. So you can see first we have to define our a naught, right? A0, which corresponds to the k equal to 0 frequency, which is a constant value. So that's what I have done over here. And then obviously we wrote it in terms of a naught by 2, not just a naught. And over here I've used a for loop to help you visualize that as the values increase from k equal to 1 to k equal to 20, our approximation will increase, and ultimately when we will reach some very large value, not 20, but 20 will also give us a very good approximation. When we will reach some value of like 100 or 200 or even larger, when it will tend to a very large value, it will almost form a hat function. So now I will plot it. Okay, so you can see that this particular black line is not properly visible. This black line is our hat function, which is varying from -3 to 3. Then this blue curve that you are seeing, this is for k equal to 1. So k equal to 1 is not sufficient. That's why it's not giving a good approximation. Then you move down to k equal to 2, which is this orange one. Then k equal to 3, which is this red one. you can see that as we are increasing the value of k, we are getting really good approximations over here. Now, how good approximations? So for that also there is another code. I'm not going to explain because this code will not be useful later on, but it's just to help you visualize. So this x-axis is showing you the error percentage, not percentage, the error. As we are increasing the y-axis shows you the error and x-axis shows you the Fourier coefficients. So as we are increasing the number of Fourier coefficients from 0 to 100, you can see that the error is really decreasing. So as we are reaching 100, it's almost going to 10 to the power of minus 3 value, which is really close to 0. But it will only ultimately reach 0 when the number of Fourier coefficients will tend to infinity, obviously. Now this is showing you the values of the Fourier coefficients. Now why it is showing like this kind of sinusoidal signal and all, it just completely depends on the what function we have chosen. We have taken a hat function which is highly symmetrical. That's why we are getting this periodic kind of function. So yeah, that's it. Now similar way, instead of hat function, we can use something called a square wave. So why am I choosing the square wave? Because there is an interesting phenomenon corresponding to this. Now, what is that? That phenomenon is known as the Gibbs phenomenon. So I have written it over here that this particular function in the beginning itself is aperiodic. Is discontinuous, is not continuous, right? So at this particular value, it's just taking a steep rise, and again, it's coming down. So when we are using the Fourier transform, the code is again the same, exactly same. I've just changed the um, function over here, nothing else. Instead of hat function, we are using a square wave. That's it, using that quarter method. So what is this steep rise showing? This steep rise means that when we are trying to decompose it with the help of Fourier transform into sines and cosines, this steep rise consists of all the possible frequencies. It means that literally all the possible frequencies from 0 to infinity, from k equal to 0 to k equal to infinity, everything is inside of that. But obviously we cannot go to infinity value because of our computational constraints. So we will see this ringing kind of phenomenon. So this phenomenon is known as the Gibbs phenomenon. So you can give it a read over here. The ringing phenomenon is the Gibbs phenomenon, which comes because of a discontinuity, and it's the error to approximate the hat function or the square wave function. Means we cannot completely determine the square wave function, which is discontinuous, with the help of the Fourier transform. Just because this steep discontinuity is coming because of the is coming because that steep rise consists of all the possible frequencies from 0 to infinity. That's it. So there is a very nice way to show it. Wait, I will try once. I will reduce the figure size. Just a second. 6,6 would be better. Mm, yeah. So see, this is for k equal to 0. So I already told you that k equal to 0 means just a naught value which is constant, right? Now if I increase this, now see closely. If I increase this is the first one. Then second, it's giving you a nice, it's coming to what we need, right? Then again. As I increase the value, the ringing phenomenon is decreasing. You can see that, right? Here it's really big, then it's decreasing, and ultimately when I'm reaching a larger value, but it will never exactly form the square wave unless and until I reach the infinity value for k. Okay, so if anyone has any questions till now, they can ask me. Is everything clear till now?
How are these Fourier coefficients exactly?
Oh, okay. I will look at them. So yeah. Tell.
Okay, so my question is that, like, how are these Fourier coefficients exactly determined? Like, from what I heard, like, I could deduce that this sequence of these coefficients should also be like convergent in nature, right?
Yeah, so as I mentioned, like I'm not going into too much mathematical details. The simple way to understand is that we have a particular function f of x or a signal f of x or f of t, and we are trying to decompose it in an orthogonal basis, which is uh, cos cos and sine. So cos and sine form an orthogonal basis. So there is a wait. I've written something related to that over here. I'll show you. Yeah. So you can see this particular part. Just a second, let me grab my pen. Yeah. So this particular thing. So when you are taking any particular orthogonal basis, you can this corresponds to our Fourier coefficient, these two values, and instead of these values we have our cos kx and sin kx. So that's what I'm saying till now, that that's how we are going to determine these values. We are understanding it in terms of the projection of that particular signal in cos and sine, and those are our Fourier coefficients ak and bk. Is it clear?
Fine.
So Ishan has a question that, so you mean that the frequency at which the red dot is at zero are the consequent frequencies of the resultant frequency? Not really. See, that red dot example I took in terms of the center of mass. So that red dot example is just it's not Fourier transform. So please not relate it to that. It's just a kind of what to say, like it's just to give you a mathematical intuition. So yeah, you can say it in that term, that those red dots are basically telling us is kind of the Fourier coefficients. That's why the peak is coming when the center of mass is far away from zero. So you can say it in that terms, but that is not exactly the Fourier transform, the thing that I explained. Any other question?
Actually, one last question regarding,
Yeah, yeah, sure.
yes. Like we had added an extra term of a naught by 2. So is that like some
Yeah.
sort of correction factor? Okay.
No, 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 no. See, k can go start from zero and all the way go to infinity, right? So we have cos kx plus sin kx, right? Ak times cos kx plus bk times sin kx. Now, if we are putting k as zero, what we'll get? We'll get cos of ak times cos of 0 plus bk times sine of 0. Sine of 0 is 0, cos of 0 is 1. So that is just a constant term. That's why we are adding it just previously itself and not taking it inside of that sigma, nothing like that. Because it's just a constant. You can see it in this particular graph also, that when I'm keeping it at 0, see right now it's at 0. So it's just a constant value, right? When I'm keeping it at 1, you can see that just single span. Is it clear?
Yes, got it.
Okay.
Actually,
Anyone
like
else?
another,
Yeah,
the a
yeah,
naught
yeah.
corresponds to the amplitude of like the wave in question or the function in question which you are trying to approximate.
No, 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 no. You're not getting. See, in case of Fourier transforms, what or Fourier series, what we are doing is we are going from k equal to zero frequency. We are starting from k equal to zero and going to all the way to k equal to infinity, right? So we have just added that is not an extra term. We have just added the term corresponding to k equal to zero in the beginning itself, because that is a constant value, and that does not have any cos or sine component. Kind of. That's it.
Yes, I understood the role of that. It's like that
Yeah, yeah.
a naught exactly, like it stands for the amplitude of something in this case.
Not really.
Okay.
Yeah. Okay. So I'll move forward now. So now we will move towards something called discrete Fourier transform. So there is continuous Fourier transform and discrete Fourier transforms. Discrete Fourier transforms are really, really important, because from here only we will move forward to the fast Fourier transforms. So if you have understood till now, the rest of the part is pretty much easy. So let's move forward. Yeah. So till now we were talking about the Fourier series. So if we are moving towards the Fourier transforms, the only difference between Fourier series and Fourier transforms is that in case of Fourier series, we deal with a continuous and periodic signal. So this particular graph corresponds to the Fourier series case. But in case of Fourier transforms, we can deal with signal which has only one spike overall, and we will have to compute it from all the way from minus infinity to plus infinity, and it's not repeating it. Okay, that's it. Everything else remains same. So we are taking that this thing also we have derived before. So sigma k goes all the way from minus infinity to plus infinity. Ck times we were taking psi k before, so it's the same thing. I k pi x by l. Sorry. Uh, and then what is omega k? So omega k, omega is something we will use to define the fundamental frequency. That's it. So I will come to that later on. And delta pi is pi by L. So what is, sorry, delta omega is pi by L. So what is delta omega? Delta omega means that difference between two. Now, if we want to find out Ck over here, now we are moving from this discrete notion to continuous notion, right? So Ck would be limit delta omega tends to 0. So instead of writing L tends to infinity, delta omega is pi by L. So we can, if L tends to infinity means delta omega will tend to 0. So here delta omega tends to 0 and it goes from k equal to minus infinity to plus infinity. And what is this delta omega by 2 pi? So it is again coming from that preceding factor of 1 by L or something. You can check it out. And here it was from minus L to L. So since it was from minus L to L, here it's minus pi by delta omega to plus pi by delta omega, because it was from minus L to L. So you can use this and put it over here. Similar changes you can make over here, f of delta, d of delta. Now what is this first part? So this delta omega, we can write it as d omega if we have very large number of points. And then here minus pi by delta, since we have so we have very large number of points in this case, and this first part, f of delta e to the power of minus k delta omega, this particular part is nothing but f hat omega. So now instead of using the word using ak and bk, we will use something like f hat of omega. That's it. Okay. So this is the main difference between the Fourier series and Fourier transform. So you can go through this particular derivation, and here this e to the power of I omega x comes from here itself over here, and 1 over 2 pi comes from here, 1 over 2 pi. Minus infinity to infinity first once for k, and again from this. That's it. So when you will simplify it a little bit, you can see that if you want to go from a time domain, so here I am using x, but this is basically, let's say this is time domain, and we are moving to something called frequency domain, right? Omega is, we generally use in physics, omega is angular frequency. So we are moving to frequency domain in this case. And this capital F signifies the Fourier transform. So when we are taking the Fourier transform in the time domain, we are moving to the frequency domain, which is denoted by f, which is denoted by f hat of omega, f hat of omega. And what's the formula for this? So you can see from here itself, f of x into e to the power of minus I omega x times dx. The same thing. This is what f hat of omega is, right? So that's what I've written over here. And in the other case, if we take the inverse Fourier transform of f hat of omega, we will get f of x means the original signal itself again. So that's what IFFT shows, inverse Fourier transform. We have written FFT, which is fast Fourier transform, but it should be in IFT, which is inverse Fourier transform. Yeah. I will come to FFT after 5 minutes. Yeah. So it is just leftover term. So here we have a 1 over 2 pi term, then minus infinity to infinity from over here, then f hat of omega, e to the power of I omega x d omega. That's it. So this is really, really interesting that if we have a particular signal, first we can take the Fourier transform, we can find out the constituent signals or hidden frequencies behind that. And then somehow we can take the inverse Fourier transform of that, and we can get the original time signal again. So it's pretty interesting, right? Now, let's talk about a discrete Fourier transform. So I told earlier that omega n is defined as e to the power of minus I 2 pi I by n. So this omega is the fundamental frequency. And this formula I am using from before only. So let's say we have some signal f, and we are sampling it from x0 to xn minus 1. x0, x1, x2, it's going all the way till xn minus 1. And these points are f0, f1 till fn minus 1. This is f hat of k, which is the Fourier transform, Fourier coefficients, and this is fk, which is the original one. And 1 by n, instead of using 1 over 2 pi, we are using 1 by n, because now the signal varies from x0 to xn minus 1, means total we have n number of points. So 1 by n is that factor, right? Now I am telling that e to the power of minus I 2 pi by n, this particular thing is what? It is fundamental frequency, right? So now we will define something called a discrete Fourier transform matrix with the help of which we can easily go from the original time domain to the f hat domain, means the frequency domain. So how this weird matrix is coming? Very easy. So you can see that. Okay, I will use some other color over here. We don't have space. Anyways, so just see closely. So e to the power minus 2 pi I by n is omega n, right? And this particular matrix is an, let's say, n cross n matrix. It has n square elements, right? So if it has n square elements, this e, if I remove the e to the power of minus I 2 pi by n, this will just become sigma j equal to 0 to n minus 1. I'm talking about f hat, right? F hat. Sigma j equal to 0 to n minus 1, f of fj omega to the power of j times k. Okay. Similarly, fk will become 1 over n sigma j equal to 0 to n minus 1 fj hat, again omega to the power minus j times k. Fine. Now look at the first one, the f hat one, because we want to calculate these, right? F hat we want to calculate. So this first term corresponds to the value of j equal to 0 or k equal to 0. So if we put our k equal to 0, this thing will become 0. This whole first row corresponds to k equal to 0. So as long as we are putting k equal to 0, this whole term will only give 1. So 1, 1, 1 we are getting like that. Now if we move on to the second row, the value of k will become 1 in this case. Okay, value of k is 1 now. Now if the value of k is 1, but j is 0, okay, in this particular case k is 0, and in this column j is 0. So if we are putting j is 0, again this will give us 0, 0, 0. So we will get again 1, 1, 1, 1, 1. Look at this one. These are the matrix elements, okay? And this fj is written over here. Now see, how can we write the second row? So first term we got 1. What about the second term? So second term is j is equal to 1. So we'll put j equal to 1 and k is anyways 1. So in that case, it will become omega to the power 1 times 1, which is just omega. Then again here you will get omega square. Then you will get, because k is equal to 1 and j is equal to 2, right? So you'll get omega square. And similarly, you will move on to omega to the power n minus 1. So in that way, you can define this whole matrix, which is omega to the power n minus 1 whole square. This particular matrix is known as the discrete Fourier transform matrix. So I will show you with the help of code also how we can write it. So yeah, I think you can see now. Over here, the first few lines again are setting the figure size, defining the libraries, setting the font size, and then we are defining the number of samples. So let's say 256. So if n is equal to 256, then we have a matrix 256 cross 256, right? Then again, omega is defined the same way. E to np dot exp means e to the power of something, exponential. Minus 1j in Python simply means 1j simply means iota, square root of minus 1. Then e to the power of minus I 2 pi by n, the simple way that we have defined earlier. Then the way we did it earlier in case of Fourier series, we were defining a whole row which was initially fully 0. Now we are defining a matrix which is initially fully 0, n cross n. That's what np dot 0 is, n cross n. Matrix which is square matrix of dimension n. Now there are two ways of doing it. I am leaving this first way, which is pretty easy. You are just running through two for loops. You are iterating through two for loops and going through each and every element of I and k. Sorry, j and k. I should write here j anyways. So j and k, and then you're finding out each and every element one by one, which is pretty slow. So Python has another way to do that. This is the way. So here j comma k, all j comma k is simply the different coefficients, the indices. So here np dot mesh grid does the same work. What it does, it simply creates an n cross n matrix, and then when we are writing dft is equal to np dot power of omega comma j times k, means it is omega to the power of j times k. That's what our discrete Fourier transform matrix coefficients were, right? Omega to the power j times k. And just for simplicity, we are only taking into consideration the real part of the discrete Fourier transform matrix. So this is pretty fast and this is pretty easy to understand. That's why we have included this as well. And what is this IM show? Why haven't I just simply written show or maybe just plt.plot? IM show means image. So I am converting the whole matrix in terms of an image of the pixels of this particular screen. So you can see that it's highly symmetrical. If you see closely, you can see that there are sub matrices that you can see over here. See this blocks kind of figure. It's highly symmetrical. Then some high frequency, low frequency, high frequency, low frequency, and this continuous pattern is going on throughout. Now, this particular thing you will not encounter much. This is just to give you a visual representation. And another thing to note here is that we are starting from 0, comma 0. See, 0 is on the top and going all the way to 250 cross 250. So again, it's the same thing that we are defining a matrix, which is 250 cross 250 matrix, right? If anyone has any particular question over here, then they can ask, or else I will move on to fast Fourier transform.
So like in the code for multiplying them, multiplying it by a matrix, so like you're brute
Yeah.
forcing it in a way right now. Or like
What?
during the multiplication, like you're multiplying each element one by one over there, like because it would be time consuming, right?
Yeah, exactly. So when we are iterating through, this is the case where we are going through each and every element one by one. You can see that there are two different for loops. We are going inside. One for loop is inside of the other. So this is very time consuming. That's why it's it takes some time. That's why I've written also slow and easy, because it's easy to understand. And this is a kind of way where Python does it. So it's just a kind of shortcut in Python. Anyone else? Any questions? Okay, cool. So now we will move on to fast Fourier transform. So basically, in general, whenever you have a particular signal, it's a discrete signal. And that discrete signal, if we try to find it out with the help of a discrete Fourier transform, it's time consuming, even if we use the faster method that I mentioned. So scientists in the past century have defined a new method called the fast Fourier transform, which was earlier devised to calculate the solution of something called heat equation. So I will come to that later on. Like I've added the code and it's pretty advanced. So I will explain you how you can use fast Fourier transforms to calculate the derivative of a function. And with the help of derivative, you can solve any partial differential equations as well. So I've added the code. You can have a look later on when you are comfortable with everything else. Okay. And in the collab, I've shared some links, so you can go through those links as well. It will be pretty helpful. Yeah. So why we are moving to fast Fourier transform? So yeah, I showed you that that particular DFT matrix has n square elements. So it's n cross n, right? What fast Fourier transform does is that it just jumbles up the matrix element in such a way that we are going from n square elements to n log n elements. Okay, so how n log n is better than n square elements? So I have written one code for that. Just a second, I will show that as well. Mm, just a second. Yeah. So here is the code. So this shows you the difference between, okay, if I go through the code, it's pretty simple. I've just defined one array from 1 to 100, and then I've defined two different functions, n square and n log n. That's it, and I've plotted both of them. So this is n log n, the blue one, and the red one is your n square. So you can see that n square is pretty big. So if you are taking, let's say 256, so 256 cross 256 is really, really large, and n log n is almost linear. It's really, really small. That's why it's very, very efficient if you are doing it numerically, the fast Fourier transform, not the discrete Fourier transform. So how do we do it? What is the algorithm behind it? So I'm again not going through the mathematical proof. This is just a way to understand it. So over here, we have this particular column, which is f hat, right? This particular column is is going from f0 to fn, which is our original timestamp. And this is a DFT matrix. So let's say that this DFT matrix is capital F. Let's say this is capital F. So we can write this whole equation in a concise way as f hat, which is this thing, is equal to capital F, which is the Fourier transform, times small f, which is our original time star. Now, instead of taking the whole DFT matrix, what we are doing is that, first of all, this is small f, but instead of directly taking from f0, f1, f2 to fn minus 1, we are writing the f even elements first and then the odd elements. So what do I mean by that? I will come to that in just 1 second. And this capital F, this matrix, I am writing it as 2 cross 2 matrix. So, okay, not 2 cross 2, like it's again uh, I512 means the identity matrix. So, why 512? I'm just assuming that this has 1024 cross 1024 elements, for example, for just for now. So, this is 512 cross 512 matrix. Okay. So, when we have this 512, what are the elements? So, this I512 simply means the identity matrix, right? What is this minus D512? So this D512, okay, this D simply is a matrix of 1, omega, omega square, and so on till whatever value you are getting at the end, and everything else as 0. Okay. And this capital F512 similarly. So what, this is again a diagonal. This is a diagonal matrix. This is not fully diagonal, but the individual blocks means this I512 is diagonal. This minus D512 is also diagonal. This is also diagonal. This is also diagonal. We know that multiplying two diagonal matrices is pretty easy, right? So let's move on to what do I mean by F even and F odd. If I'm just taking a very small example. So if I'm going from F0, F1, F2, F3 till F7, which has total number of elements as 8. First, we will take the indices which are even. So what are the even indices? 0, 2, 3, sorry, 0, 2, 4, 6. So that's what I've written first, which is F even. Then 1, 3, 5, 7, which are the odd elements. Now from 8, we have reduced the number to 4 cross 4. Just as I'm writing over here that from 1024 cross 1024, we are moving to 512 cross 512, right? Then from this 4 cross 4, take the first one. Now in this first one, this one is even, this one is even, this one is odd, this one is odd. So again, this is F even. 0 and 4 is F even, 2 and 6 are F odd. Then 1 and 5 are F even, and 3 and 7 are F odd. That's what I've written. So now again, this has two elements, again 2, again 2, again 2. So now each of them are two, will correspond to a 2 cross 2 matrix, right? So now see, we will, with the help of FFT algorithm, we will start from a very big matrix. What is 1024? 1024 is 2 to the power of 10 cross 2 to the power of 10, which is pretty large. And then we are moving all the way to F2, which is nothing but a 2 cross 2 matrix. So solving a 2 cross 2 matrix, that number of times is not a big deal for us. So that's why this algorithm is pretty good. And even if you didn't understand this, you can go through this again and you can try grasping it a little bit. And this is not the actual mathematical proof. I will move on to the code now. So code is pretty simple. Uh, just a second. Yeah. So the first thing that we are going to learn now, which is really, really important, especially in astrophysics and in many different areas. So denoising a particular signal. How can we use fast Fourier transform to denoise a particular signal? So how will we do that? So what we can do here is that first we can use some easy examples. So let's say we have a mixture of signals. Which example should I take? Okay, all these codes are there. Okay, so I'm taking an example where we have a mixture of sine and cosine. So my first frequency is 10, second frequency is 20, and amplitude is 1, amplitude is 0.5. So I have taken different amplitudes as well as two different frequencies. And then I'm defining a signal, arbitrary signal. In your case, when you will be using, you will get some timestamp. For example, in case of astrophysics, you generally get a particular, what do we say? You generally get a discrete signal of time versus flux. Flux is the power. And then you incorporate it into this. And but here I'm not using all that, so I'm just arbitrarily defining some random signal. That's what this is, with the help of two different frequencies. Now basically all the languages have these packages to perform FFT. Here the command is simple, np.fft.fft. So this will, FFT means fast Fourier transform. Okay, so transform the f hat values. These are calculating the f hat values. This is simply equal. We have this signal, which are the f values, the f vector, column vector, and then we are moving to the f hat domain with the help of this transform. How do we do that? Simple, np.fft.fft of that signal, we will get f hat values. Now we have the f hat values. Now to plot that f hat values, we need these frequency values of x-axis as well, because earlier we had time value. So you will have to convert accordingly your time values to the frequency values as well. So how will you do that? Again, another simple command is there, np.fft.fft freq means frequency, and you just put the length of the signal, and d means the timestamp, like how, what is the difference between first and second signal, the delta x that we were defining, b minus a upon n minus 1, that kind of thing. This is delta t, the sampling rate, you can say. Okay, this is just to find out the frequency array of the FFT, and let's just plot it. Okay, so you can see that this is our original signal, the original signal, and you cannot really guess just by seeing this amplitude versus time signal that what all frequencies are underlying this. But just by writing two lines of code, we found that there are two different kind of frequencies. This is the first frequency, this is the second frequency. General question that you should have right now is that why there are four peaks. So I'm taking a symmetrical wave in this case, and I am taking only the positive components. That's why I'm getting the same values in the positive as well as the negative domain. Both are the exactly same values. If you will take real and imaginary different, I'm coming to that. Here you can see that I've taken real and imaginary separately. So I've just defined it in that way. You can see that amplitude imaginary times 1j means basically iota times something. So we have both separate. So now the frequency domain that we will get, the Fourier transform curve, fast Fourier transform curve that we will get, will not have exactly symmetrical in positive and negative x-axis, because now real and imaginary parts are different, because we have taken complex signal. So here you can see that both had different frequencies. Right one correspond to the real one, left one correspond to the imaginary one. As simple as that. So now let's move on to this. So we have this particular data. Okay, this is the kind of data that you find out in general cases. So I will show you something. uh, just a second. uh, light. Hmm. Show you just a second. Yeah, so can you see this particular kind of curve? So this is the kind of light curve that we generally see from stars. So uh, what this y-axis basically shows the power, the flux in power, in parts per million, ppm, and this y-axis shows the frequency, or the sorry, y-axis shows the time. This is as simple as it can get. So there is a telescope called the Kepler telescope, and this data has been taken exactly from that particular telescope's data itself, where the y-axis shows there is a star, the name of the star also I can tell. Just give me a second. Yeah, the KIC ID for this star is 9993367. So that is kind of ID. I guess it's Kepler 71 or something. It's name of a star, and this is the kind of light curve that you generally see. And now we want to find out what is the underlying frequencies in that light curve. So that's what you can see over here. But this is not Fourier transform method. But yeah, I'm just giving you a flavor of that. Now, okay, so I was here. So you have a noisy signal over here where y-axis is your power and x-axis is your time. This is very noisy signal, and you can see over here that there is the black one is the underlying frequency, but in reality, as same as the example that I showed you, you will only see the red signal, not the black one. So I'm just giving you a kind of spoiler over here. Okay, so we want to find out, we want to separate, remove this whole noisy component. Okay, so this code is just to write this. So what I've done, I've just defined a clean signal over here, and then I have randomly, you can see that there is a nice Python code for that, np.random.random, which basically creates a random Gaussian Gaussian white noise. That's what I've added it over here with the help of FFT command. So here it's f hat. F hat means the same f hat that we were talking about. We will have to input two different things. First one is the f, which is your signal, along with the noise, means the signal with the noise, and this n is your time step, the length of the whole data, not the time step. Sorry. So n, it's written over here that n is equal to len of t, right? And this is just to calculate the PSD, means the power spectral density, and then I've just plotted it, the clean data, because since I've taken the Fourier transform now, I should be able to see the clean data. If not the clean data, at least the spikes in my frequency domain. So remember, this is our original data, and after taking Fourier transform, it looks something like this. So see, these are the underlying frequencies, and this is the noise. See, we have completely removed the noise. It's so low. Now, I am still not satisfied with this. I want to remove the noise completely. So what I can do, simply, we can remove all the values of the PSD, means power spectral density, that are less than 100. Okay, so I'm only taking the value which are greater than 100. So you can see that this is the 100 value. I'm taking only the frequencies which are more, which corresponds to the power spectral density of value more than 100. So when I'll do that and again replot, you will only get the clean signal, which is the blue. And now you can filtered signal, the blue one. Okay, basically that's it. Now, one last thing that I'm going to cover today is how you can calculate the derivative using FFT. So let's say you have a function f and you want to find out the derivative of that particular function. Before moving forward, I want to tell that we are using two different kind of frequencies for this example, because that's what the convention does. First one is kappa. Kappa is the spatial frequency, means frequency in the space. Spatial frequency means in the space domain, and omega is the temporal frequency that was in the time domain. One more task or kind of homework, you can say that this particular thing, when you will calculate, means the Fourier transform of a derivative of a function, when you will do it manually using the initial formula, you will get something like this. Means you will get iota times kappa, means the spatial frequency times the Fourier transform of the function itself. Now, what is the Fourier transform of function? This is nothing but the f hat, right? We know that f hat is equal to capital F times, sorry, capital F times f, our signal. That's it. So this is nothing but the f hat value, and I times kappa remains same. What is kappa? It varies from k1 to kn, or you can say that from k0 to kn minus 1. Now listen closely. This I is common for all, so I'm taking I outside. This is again a matrix, a column, where first value is k1 f1 hat, k2 f2 hat, where we are going all the way from the lowest frequency kappa 1 to the highest frequency kappa n. Now you will ask, how can we find out derivatives? So it's pretty easy. When we are finding out, let's say we know what our function is and we want to find out the derivative of that particular function. So what we'll do, we'll just take that function, we will use the FFT algorithm to find out the f hat values. Okay, I've written the steps also, f hat values. When we will find out the f hat values, obviously we will have the kappa 1 to kappa n values as well. We can easily find out this particular thing. When we can find out this particular thing, what is this? This is equal to the Fourier transform of derivative of that particular function. Now, if I take the inverse Fourier transform of this particular thing, df by dx, what I will get? I will get df by dx itself, right? If you will take inverse Fourier transform of the fast Fourier transform itself, you will get again the same signal. That's what the thing is, right? So again, I will repeat, you have a signal, you want to find out its derivative. So first you will find out the Fourier transform by using FFT algorithm, then you will calculate this particular thing. and after that you will just take the inverse Fourier transform to find out the derivative of it. Pretty easy. Now I will show you that it actually works. Okay. So yeah, let's see. So what I'm going to do here is that I'm taking a random signal, which is a Gaussian wavelet. Everyone knows what Gaussian wavelet is, like, right? It looks something like this, and the formula for Gaussian wave is e to the power minus x square by 2, or you might e to the power minus x square by 2 times some amplitude factor and all. So I'm taking similarly the Gaussian wavelet has additional factor of cos kx as well. So what is Gaussian wavelet? It's same as Gaussian function, just that in the in place of amplitude we have a term of cos which is getting multiplied to that. Then I manually calculated the df. Df means df by dx, which is the um, manual derivative. Means I calculate the derivative. You can easily find the derivative using pen and paper, and then I've written that. Then I've plotted it. Simple. I have done the same thing using fast Fourier transform. So what was the algorithm? We have this particular function, right? First, we will find out the fast Fourier transform of that function. So see, np.fft.fft. I found the fast Fourier transform. Now we will find out the kappa values. So here are the kappa values. 2 pi by L times that whole array from minus n by 2 to n by 2. We were taking from minus L to n. Same thing. Now, what is it np.fft.fft shift is doing? What this does is like this takes the kappa and it arranges. Like sometimes what happens is that I've calculated FFT separately, like f hat separately, and I'm defining the kappa separately. So sometimes it get the kappa 1 indices should exactly match with the f1 hat indices. One should match with one kappa 1 with f1 hat, kappa 2 with f2 hat, and so on. So that's what with this fft.fft shift does. It arranges it in that way, that kappa 1 f1 hat, kappa 2 f2 hat, and so on. And then I'll again take the inverse Fourier transform with the same. What is the Fourier transform algorithm? In inverse Fourier, what is the fast Fourier transform case? np.fft.fft. Inverse Fourier transform is np.fft.ifft. That's it. So that's what I've calculated. So I should technically get my original derivative, right? So here you can see the black one is true derivative and the red dotted is the fast Fourier transform derivative. Exactly, it's matching. So that is basically really good that you can use the FFT algorithm to easily calculate the derivative of a function. Now you can use this thing because we know that partial derivatives are kind of these derivatives itself, but in a more complex way. So I've written this code over here with the help of which you can find out the partial derivatives or solve the heat equations and all with the help of this.